So for our conclusion of lesson 6, you may have realized from doing our tangent lines and our instantaneous velocities that we are looking at the same limit. It does have two different forms we looked at, but ultimately they're the same thing. And so we're actually going to give it its own name and use it in ways beyond just slopes of tangent lines. So the definition here that we're going to be talking about is the derivative. That is what we are going to call it. The derivative of a function f at a number a. Just going to underline that. That is what we are defining. Denoted, it has its own notation, which looks like an apostrophe. Okay. And we read that apostrophe as a prime. So we read this whole thing right here as f prime of a. Okay. Is exactly what limit we've already been dealing with. Usually the definition is given with the h form. So the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, and of course, if this limit exists, okay. But alternative, I can't even say the word, alternately, I don't think that's the right word. Whatevs. Here we go. You could also do it as the limit as x approaches a of f of x minus f of a over x minus a. Okay. So that is still a way to calculate the derivative of f at a. It's just more formally or more usually commonly done with the h's approaching 0. I think algebraically that version works out more often. So it just tends to be the first one we use. And then just be sure to note that this calculation has still come from the same place. So f prime of a, the derivative of f at a, is in fact equal to the slope of the tangent line to f of x at a. So that is one immediate interpretation of the derivative, is the slope of the tangent line, okay, to the curve. Okay, so for a couple of examples here, we're going to start by finding the derivative of this function f of x equals the square root of x. And instead of giving you a specific number, we're just going to leave it in terms of a at this point. You'll see at number 2, then we're going to just take the same function and plug in a equals 4. But so we're going to do it generally first here, and then plug in the 4 down there. So this shouldn't be any different than the calculations we were just doing. F prime of a is the limit as x approaches a, f of a plus h minus f of a all over h. So we're going to substitute in, oh, wrong, sorry about that. I put the two, I put the two parts together as opposed to keeping them separate. So I am doing the limit as h approaches 0 of f of a plus h minus f of a over h. All right, so the limit as h approaches 0. F of a plus h is just the square root of a plus h. F of a is the square root of a. So we have arrived at the 0 over 0 moment. I cannot factor this, but what other strategy have we talked about, have we done in the past in lesson 4 that could help us out here? I'm hoping that in your head or out loud, you are saying multiply by the conjugate. My square root of a is a little rogue there. There we go, a little better. So how did I know to do that? Because I can't factor, I can't simplify, and I do have two terms here, one with square roots, so that this conjugate will get rid of those square roots up there. So I'm going to come down here to the limit as h approaches 0. Multiplying out the top will just give me the a plus h minus a. Remember, it's a difference of squares. So it's just going to be this squared minus this squared. And then remember, we leave our denominator written in pieces. We rarely multiply out the denominator. A's cancel on top. And then look what else cancels. I have an h left here and an h there. So my h will cancel. And now I'm ready to plug in my 0. So when I plug in my 0, my limit notation goes away. And what is the square root of a plus the square root of a? It's 2 square roots of a. So this is our derivative of the function f of x equals the square root of x at a. And the second problem is just asking me to plug in a equals 4. Oops. So f prime of 4 will be 1 over 2 times the square root of 4, or 1 over 2 times 2. You know what? I did it again, didn't I? It didn't just say find the derivative. It said find the equation of the tangent line. The equation of the tangent line. So if I want the equation of the tangent line, I need to do y minus the y coordinate equals slope times x minus the x coordinate. What is the 1/4 in that equation? It's the slope of the tangent line. 4 is the x, so I need to probably just plug that in here to figure out that my y would be 2. All right. Reading my directions is always a good idea. Equation of the tangent line. So when I need that, I need to use the derivative as the slope and then the point of tangency. All right, so here's one for you to try. Find the derivative of this function at that given value of x. Press pause and give it a go. All right, we ended up with another complex fraction, didn't we? So I started off with my general limit, plug in the 3 plus h, plug in the 3. Now I have a complex fraction. I have this subtraction of fractions in my numerator. I use the same technique I did before. So I can see that my common denominator here will be 3 times 3 plus h. So I'm just going to go ahead and multiply this whole thing on top by that and the whole thing on bottom by that. Because when I multiply this times this, the 3 plus h's cancel and I'm left with just 3. And when I multiply it by this, the 3's cancel and I'm left with just 3 plus h. Careful that I have to subtract that whole thing, so I need to distribute my negative. And then I'm just leaving those things multiplied as factors in the bottom. Distribute my negative, my 3's will cancel, and then my h's will cancel. And then I'm able to plug in my h equals 0. Okay, so the algebra of these limit calculations cannot be overstated. You have to be able to simplify and work with these things algebraically. So if that's something you need extra help with, you need to ask now, because these problems will not go away and you will have to be able to demonstrate that kind of algebra. Okay, one more question here, following along the same idea of the interpretation of the derivative as the slope of the tangent line. Here is a graph of g of x, and you are going to try to put these numbers that are listed here in order from smallest to biggest. So one of the numbers is just plain old 0. The next one is g prime of 2. So what that means, if you want to go over to the 2 on the function and you want to kind of think about the slope of the tangent line there. I mean, it's positive, right? So it's definitely going to be bigger than 0. Let's look at the others. So that was this one. Let's see about g prime of 0. So here's where g of 0 is. And if I look at that tangent line slope, well, now that's negative. So this one is definitely going to be less than 0. G prime of 1. That looks to be maybe a little bit less steep than the g prime of 0. I realize we're kind of eyeballing here, but this one to me seems like it's less steep, which would make it less negative and therefore a little bit bigger. And then g prime of 3. Oh, that's way up here. We're talking about a very positive number. So if we're going to look at smallest, I think we'd probably start with g prime of 0. Next biggest would be g prime of 1. Then the 0, since these two are both negative, followed by g prime of 2, and ending with g prime of 3. This would be smallest to largest, just based on kind of eyeballing which tangent lines are uphill and downhill. That's easy to eyeball. And which ones are steeper than the others, okay? Because the derivative is equal to the slope of the tangent line at the point.